Okay, so yeah, so now we're okay with the first part you're telling me that we can figure out how long it takes to hit the ground. 'Cause
Yeah.
we just look at the vertical component of gravity, right?
Yeah.
Okay. Or the vertical component of the motion, which is,
And do the big mama.
right, okay. And then we know how far the stone lands from the cliff because if we know the time, yep, times the horizontal component of velocity, that's no big deal. But the last part is a little tougher, right?
Yeah.
Okay, so here's the last part of this one. Here's what we're trying to do. With this last one, we're trying to fill in. I'm running out of virtual ink. This is, okay, so we've got an X part and a Y part to our motion, right?
Yeah.
Yeah, this is really struggling. Okay, so what are our kinematic quantities in the X direction? Well, we know some stuff. We know that the velocity is the same the whole time, right? And that's 13.3.
Wait, is it V not X? It's just.
Well, it doesn't really matter because it's the same always. So V naught X and Vx, they're the same thing, right? Okay, but that's not the case with the Y component of the motion, the vertical component.
Yeah.
There we know that the initial velocity is 0. A is negative 9.8.
Bless you.
We found
The distance is.
displacement, good, so we know displacement is negative 61.8. We found time, right? It equaled something. Oh, right there, okay, we found it, 3.55. But really what we're trying to find then for the last part is V final. Okay?
Yeah.
So let's find that. So if we know, we don't even really need the time, do we? We could just use the bottom equation and solve for V, right? We could use the equation V sub y squared minus V naught sub y squared equals 2a delta y. That should just be delta y, right? Does that make sense why we call it y this time? Because it actually is vertical, so might as well call it y. And so this is 0, so V sub y is just the square root of 2a delta y, which we can calculate.
That's how you find it?
That's how you find the vertical component. Okay, so the vertical component would then be square root 2 times negative 9.8 times negative 61.8. Which is that, 34.803, blah, 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 right?
Yep.
Okay, so we can plug that in. Okay, so what did we just find? So if we've got the vertical component and the horizontal component, those are the two components of the final velocity, right? Those are the components of the velocity of the rock when it hits the ground.
Wait, why isn't it just 34.8?
Because that's only the vertical component. Oh man.
But I thought that's what we're trying to find, because we're trying to find
No.
it when it hits the ground.
No, the
It's
stone
just
hits the
going down.
ground with the speed of what?
Okay.
So it's going to have, the speed is going to be, there are going to be contributions to the speed from the vertical component and the horizontal component, right? Wouldn't you agree that if let's do an example. We'll do a little experiment here. If I drop this pin from right here, hits the ground with a certain speed, okay? Now I'm going to throw this, I'm going to wing this pin horizontally and tell me if it hits the ground with a faster overall speed or not.
Well, you can throw harder.
Good reflexes. Good reflex. Again, I mean, it definitely hits the ground going faster, doesn't it?
Yeah.
Like, quite a bit faster.
Yeah.
Because it's got a lot of horizontal speed that it's carrying too, right?
Okay.
I just want to see if you're awake, Alexis.
I was waiting for it to come.
Everybody get that though?
Yeah.
So it's definitely, there's not just a vertical component here, there's a horizontal component. Well, how do we add those up? They're at right angles, right?
Yeah.
So we know that we can always add the components of a vector up to give us the vector, right? Usually we do that in reverse when we break a vector into components. right? But we can also reverse that process. So now we've got this horizontal component of velocity, which is 13.3, and we've got this vertical component of velocity that is 34.8, and we're trying to find that, right? Because that is our V final.
Okay. Got it.
Make sense? Okay. Any questions on so that is the last assignment?
Yeah.
Okay, otherwise, does that unstick you?
Yeah.
Okay.
What was the answer?
So the answer would be, well, we can figure it out. So the answer would be the square, oh darn it, I don't want to do that.
What? Oh, because you got rid of all
Can't
your
you just
answers.
go up and
I think
it'll?
I
That's
can
okay,
just
we
go-
can do like approximately.
Oh, there it is.
Oh.
There it is, right there. So we've got the square root of that number squared plus 13.3 squared.
Yeah.
Right, Pythagorean theorem. And so the answer is 37.3.
Woo.
Okay? And is that what this thing was telling us?
No.
37.2
2.
it says. Okay, and that was the one that was wrong though.
Yeah.
Remember that was the one. Yeah.
Okay.
But now it's fixed, so it would work now.
Oh, got it.
Okay?
How do you do one of those tension ones? Like, I know how to do these later ones, but on the first,
Okay.
on the very first, very first problem.
Okay. Yeah, let's go through attention. So, like the first problem set you said?
First problem, set, like 7.1 or whatever it is.
Okay. All right. Okay, let's do one of these. That one?
Yeah.
Okay. Can anybody read that one?
No, it says green. Oh.
Okay, so let's.
It's just-
No, this is someone else.
I don't know whose that was. I just picked a random one.
Oh, good, okay. That was a deep secret.
Okay, so this is the stuff. Remember, this was like when we talked about the ice on the power lines.
Mm-hmm.
So we've got, if we want to draw a free body diagram here with this one, we've got here's the weight, the 433 Newton weight, right? So there's one force that's acting. 443.
Yeah, I don't like these equations. We should not have those.
Oh no, not an option.
They confuse me.
And then we've got, it's supported in a motionless position by two ropes that each make a 16.8 degree angle with the horizontal. Okay, so there's T, and there's T, right? So there's our picture. Okay, we've got to orthogonalize this free body diagram. We've got to pick our orthogonal coordinate system. So what's it going to be? X and Y. That's exactly right. So we'll go X and Y. So we'll just do a regular old positive X direction, positive Y direction, right?
Yeah.
And so to do that, the weight is already lined up vertically, so that one's already broken up into components. It's only got one vertical component. But the blue vectors we need to trade. So each of these blue vectors, we're going to break into a an X component of tension and a Y component of tension, right? Okay, so what is the X component of tension going to be? It's a component, right? It's a component of T, and so it's always going to be the vector multiplied by either sine or cosine. Okay, cosine?
Mhm.
Okay, you buy that, Olivia?
No.
Okay. It's right, but how come it's right is my question. So it's right because remember by SOHCAHTOA, we know that the cosine of an angle is the ratio of adjacent over hypotenuse, right? So we gotta remember this stuff, right? It's the ka. Cosine is adjacent over hypotenuse, right? So- So T sub x then is equal to T cosine 16.8 degrees, and T sub y, what's that one gonna be? Somebody, what's that gonna be? Deshaun? T, this component right here, there's the angle. Sine, yeah, good, yeah, because it's the opposite. Oh, you probably said that, I just didn't hear you. So T sine 16.8 degrees, right? And these would be the same, right, over here?
Yep.
Okay, so then we can now make our orthogonalized free body diagram, which is a fancy word for just saying now we've got all the components broken up into horizontal and vertical, all the vectors broken up into horizontal and vertical components. So that would look like downward, we've got 443. Upwards, we've got two contributors, right? We've got T sine 16.8 degrees, and then another T sine 16.8 degrees. And then horizontally, we've got T cosine 16.8 degrees and T cosine 16.8 degrees.
Wait, I have a question.
Yep.
Would you have to time the 443 by like gravity in the end?
No, because it's already a force, it's a weight.
It was, oh, wait.
Right, so they didn't give us the mass, they gave us the weight.
Oh.
So they gave us, notice that I should have put that in there, I need to probably change it so it reflects that, but it should be, the unit should be newtons, right?
Okay.
So now, we want to solve for T. So we've got two equations of motion here, right? Remember that we've got these perpendicular or orthogonal directions, and so we can sum the forces horizontally and sum the forces vertically, and they both need to add up to the horizontal and vertical components of the net force. But what is the net force?
For Y,
440.
for Y or for X?
Well, for both.
0.
0 because it's motionless,
Oh,
right?
that's right.
Yeah, so it's in equilibrium, isn't it? There is no acceleration.
Oh, I just figured it.
So then our equations of motion are gonna look like, we've got, this one is kind of a wasted one.
Yeah, we don't need the X.
We don't really need the X, do we?
No.
The X is just, all the X is gonna, I won't even write it, it's just gonna say that
Blah, blah, blah,
Yeah.
blah, blah, blah.
this minus that is 0, right? Big deal. So that's useless.
Useless.
But F net sub Y, that does tell us something. That tells us that this plus this, because those are both positive, so in other words, 2t sine 16.8 degrees minus, that's negative because it's pointing down, right? Minus 443 equals 0. So I can solve for t, right?
Yeah. Right.
Okay, make sense?
Mm-hmm.
Well, we got it.
That's it.
Okay, that's it.
And, okay. Got it. Okay.
Okay, good?
It's not pretty good.
All right.
Wait, so,
It's just,
what was the original question? Can you go back up to that?
So the original question just wants the tension in each rope, so we're just
So you
solving.
just add up all you just put T in for all those different tensions, and then you just add all of them together?
Well, so all we're doing now is algebraically isolating t.
Yeah.
So what would I do to get t by itself?
And then that's, T is.
Is the answer, yeah. T is the tension in the ropes. And look what, if you look at this vector here, you've got this big tension, but only a small part of that tension is being used to vertically support the weight. A lot of it's just being wasted to, pull against itself, right? Okay, and that's why, remember, that's why like ice on power lines is so dangerous, because it creates a tremendous amount of tension when you have to support even a moderate weight. Okay? All right, so for today, tomorrow you got a lab day. For today, let's talk space travel a little bit. Okay, but it's, now hang on, don't get too excited. 'Cause we're talking space travel for a reason here, because it relates to the
Are we
next
gonna
topic.
space travel ourselves?
Well, kind of, yeah.
Oh.
So you guys get to design here. I want you to think about a way that you could design two things. We got to consider space travel in 2 ways. We need to consider long-term, like space habitation, maybe even just like in orbit or something. Like say we need to put a bunch of people in orbit around, maybe the moon, for example, to mine the moon. Okay, so
Pretty lame.
looking into the
Maybe
future. here.
Mars, that's more exciting.
Mars more excited. We'll go Mars. Okay,
Yeah.
we're gonna go mine iron ore from Mars. There you go. Okay, or the other thing you might want to consider is maybe we're going to envision a time when we are going to, climate change it's running amok, and the planet is starting to become hostile and hostile environment, and so we can see that the end is at some point going to be here, and so we've got to send humanity off on this long distance journey to a new solar system, right? And to do that, we've got to put them in this spaceship that's going to take, maybe millennia to get to its destination. So whole generations of people are going to live on this spaceship and know nothing different. So we have to design a spaceship that will accommodate them, right?
Yeah,
So there's some things you have to take into account, though. Space is not, people have not evolved to live in space. It is not a friendly environment for us. When we go into space, for even short periods of time, it causes serious health degeneration for astronauts.
Like mushy bones or something?
Yeah, that's the main thing that happens is bones, you get a significant bone density
What
loss.
causes that?
What causes that is the fact that there are no compressive or shearing forces in the bones, and the osteocytes in the bones, they respond to forces to regenerate themselves, and so in the absence of that, they just weaken and
Because we don't really need them in space.
kind of, yeah, because they're not responding to any stress that's saying we need you to be strong. And so literally, if you were out in space for an extended period of time, and then your own weight would just snap your bones when you stood on the ground. And so that's a big problem. And it causes your muscles atrophy, it causes congestive heart failure, it causes all kinds of problems. And so people that are in space for extended periods of time, they have to go through a grueling regimen on a daily basis of really hard exercise, resisted exercise, where like they'll strap bungees to themselves and have to do all kinds of running on a treadmill and squats, and they've got to mimic that gravitational force. And even then, it doesn't quite do the job. And people that spend time in space, it really does. It's a lasting, potentially permanent, has a potentially permanent effect on their health to some degree.
What if you never come home? What if you stay in space?
Okay, so if you stayed in space, then it would even be worse. Then you'd eventually just die.
Oh.
And so the problem there is, obviously, what are they lacking? Gravity. Yeah, they're lacking gravity. So you guys have to come up with a scheme here to
Get
at
gravity
least
on the
simulate
spaceship.
gravity for them, so they can live. What is it again? Centrifugal force?
What?
Okay. How would you accomplish that?
What is that?
You could spin the environment. Yeah. Now you guys have done these experiments already. You didn't know this, but you were put into training at a very early age on a playground to try to figure some of this stuff out with the, because there's possibility. People were watching you the whole time, thinking that maybe some of you are going to be astronauts, and they wanted to be able to see who did the experimentation the best. And so there's probably big long files on you about how you did your experimentation at the playground. What was probably one of the main places you did your experimentation at the playground?
That spinny thing up at Rice, or not Rice, that part.
But they
Aldridge.
take almost all of them, right?
So what's that? What's spinning thing at Aldridge?
Keegan used to just fling us.
You mean like a merry-go-round? You mean?
Yeah.
That spinning thing? Oh, but it was weird shaped, okay. But a merry-go-round would work, right? Merry-go-round's a good place to
They
do
don't,
that
they want
research.
people to be astronauts anymore, that's why they take all those away.
That's right, yeah.
Or just when you just spin around in circles.
So you did notice, didn't you, that when you were on a merry-go-round, if you were, like, you know how they had those little, the merry-go-rounds all had the bars that kind of went from the middle to the outside, and then there was a cross piece at the outside that you could lean against?
Oh, yeah.
Remember that, right? So when you went out to the outside and leaned against that and it went really fast, it kind of pushed you pretty hard against that, didn't it?
You're not supposed to.
Has anybody ever gone to an amusement park where they'd have the ride that goes around where the floor
And
disappears?
you can't put your arm out because it'll hit you right in the face.
Yeah, like you can't lift your head up. You're like,
One of my friends when we were younger, he threw up and farted in front of his face.
Wait, how does that help with gravity? I feel like that takes it away.
No, that's, you can't get off of that wall, right?
Mm-hmm.
Oh.
Right? It's simulated, and that's a real thing, right? I mean, everybody that's done that would attest to the fact that they drop the floor away, and you can see the concrete whizzing by you underneath, but there's no chance you're gonna fall. You're plastered against that wall, right? It's hard to get your head even off the wall. So that effect is real, and that is probably the solution. So if you're gonna design this habitat, it's probably gonna look something like.
You need it to be really big though, because otherwise you have
do.
to spin it too fast and
You do.
with your ears.
Yeah.
And also your head would have like different amount of gravity
Then your feet, it causes problems. Yeah, so you do want it to be pretty big, but just kind of,
For
we'll talk about the scale of how big this would need to be in a second, but this is really just what your habitat would look like. It's just gonna look like, let's see,
This is so much like
let me do that.
no.
creating
Is that the one? Everyone just started. Is that the one where they drop the kids on the earth?
Yeah. Isn't it based on a book?
Yeah, there's
I
books
tried
on
to read
it.
the book.
What?
I'm sorry, Elena, I'm a book person.
What's the show?
The one that
You just love your TV. This is
What's
a
the
really
show?
cute
The
guy.
one Yeah, because it's a legend.
What do they do though?
Wait,
You send 100 people back to Earth and they're like, here, survive.
Okay, so there's your space habitat right there. That's the living quarters of your space habitat.
that's
You
pretty
guys,
boring.
it's pretty boring. You guys are just gonna
It
walk
is.
around.
Like a basketball.
It's like
Like Wally, they had like the.
That's what I said earlier, yeah. Well,
Wait, so we're not in the middle? We're
No.
only on the outside?
You're living on the outside.
You're gonna be pushed towards the outside.
living on the edge.
Okay, imagine that you put some ants inside the inner tube, inside a tire, and you spun the tire. The ants would be pushed against the outer wall of the tire, right? Well, you guys are the ants, and that's the tire, right? So we spin this thing, and you're pushed. You feel a force. You feel the floor pushing up against your body, and it feels like gravity, right?
But
Okay.
if we go into space, would we be able to walk around?
Yeah.
Yeah.
Absolutely. So
Would
you
there be
can.
less gravity?
So you guys can walk around. Well, we'll spin this thing. How about this? Here's our plan. We're going to spin this thing at just the right speed so that when you walk around inside this gray habitat, that is normal. That's regular 9.8 meters per second squared G, right?
Yeah.
But this is looking like if this is a rocket ship, we're looking, it's coming right at us, and this thing is like spinning, and probably there's another one behind it spinning the other way, right? You might have a series of these rings that are spinning in opposite directions for reasons that will become clear in the near future in physics to conserve angular momentum, but we'll get there later. But what's probably happening then is these are probably connected to, maybe there's this long axis here, like here's the tip of the rocket ship and the boosters are way back in the back, right? And so you've got these tubes
Yeah.
that you can climb up towards the middle, and then you get into this section in the middle here,
Like a steering wheel.
kind of like a steering wheel, yeah. Okay, and as you climb these ladders to get towards the middle, what's gonna happen to the force of gravity that you feel? It's gonna weaken, and you did that experiment on the merry-go-round. As you walk towards the middle of the merry-go-round, it got easier to stand, right?
You can't walk on
Okay.
No, but like on the spinny thingy, all
But if you
the,
ran.
there is in the middle.
Well, I mean, like if it has a solid disc underneath it that spins on the merry-go-round, you've seen those kind, haven't you?
We went on there, right?
Oh, I even remember those doing my experimentation days as a kid. You can walk towards the middle, and as you walk towards the middle, you can stand up in the very middle, right? And near the edge, you gotta really lean into that thing, or you're gonna fall off, right?
Carousel. Carousel.
Okay, so what could you do in here? You could practice your spacewalks and things like that, because you're gonna be weightless in there, right? Okay, but then what if you want to do some workouts? Well, then we're also going to attach some lobes down here that go like,
To make it way more.
yeah.
But why can't you just do your exercise like a normal person and then negative 920 or the 920?
Well, you could, but then NASA doesn't want to have to
Wanna be
pay to
strong.
bring all those weights up there too. They're heavy, right? That's a lot of mass to accelerate. So down here, you could just take you could climb down here with your whatever meal you're going to eat. You know, you're going to bring your bottle of water down there, and you can do bench and curls and stuff with your bottle of water because gravity's going to be so much stronger, right?
Ooh.
Pretty good thinking, huh?
Yeah,
Okay.
NASA's brilliant.
NASA's pretty brilliant. I agree.
Boy is brilliant.
Spin like a bucket full of water and it doesn't come out.
Oh, so we got this figured out, right? Okay, and there is, Ryan makes a good point. There is an issue where if you're on a contraption like this that's spinning too fast, then it causes issues. It makes you probably puke. You'd be motion sick the whole time. So I can't remember what the exact size is, but I think it has to be something like the circumference needs to be 1.2 kilometers or something like that, I believe, in order for it. I can't remember. We could look it up. But there is a size beyond which you don't even notice the rotation anymore. Okay, and so we have to just make it sort of big, but we could do that, and then spin it at just the right rate so it'll be comfortable for us. That works. That's a great idea. So then we can travel to the stars. We can have generations of people that just live on this thing, and it would be sort of normal. They
But
wouldn't.
would you have to force like to spin it?
Okay, well, sure, but then we've got these things spinning in opposite directions, and we've probably got some kind of advanced fuel system where we've got some reactor that gives us all the energy we need. Fusion reactor, there you go.
I need a food.
Well, because we're growing food out here in some of these habitats. We're actually growing food. We're creating artificial sunlight. You know, we're recycling all of our water. We're all figured out.
I hope we don't recycle all.
Oh, we're recycling all our water.
We recycle all of our water already on Earth, so.
That's true, we do.
Not in Pendleton. What do
No,
we
on
do?
Earth, every single water that's ever been used. is-
Eventually comes back.
It'd be so weird.
That's how the water
To
cycle
do that,
works.
you'd be so bored though. If that's your life, that's your habitat. It'd be so boring.
But
Sure.
What if we made
Sure.
it big and put Disneyland in it?
Yeah, but we do some fun stuff too. We've got some places in there where we can
You
learn
have
about
board
physics.
games. You can create new sports.
Oh, that
events
makes
in
sense.
that area.
The ceiling we see for
Yeah, we're like-
Okay, but here's my question. Here's my question though. So we got this good contraption here. Is this force that we're experiencing real?
No.
You mean real.
The centrifugal force that's throwing us outward into the floor.
It's not
Because
the
that's,
same
I mean,
as-
and you can experience this like if you're, okay, imagine this, we don't have to go to such exotic extremes. You guys could probably do this at lunchtime if one of your buddies has an old pickup truck with a vinyl seat that's been armor rolled, so it's real slippery, and he turns real sharp to the left. If you're sitting against the door, the right door, and there's 4 people in there, what's gonna happen to you? You're gonna get squished because all those people's centripetal force is pushing them against the outer door, right?
Yeah.
It seems like a very real thing, right?
No.
Is it a real force?
No.
It's totally fictitious. It doesn't exist.
What? What do
It does
you mean?
not.
What does
Well,
that
it
mean?
can't exist because a force. Think about what we've said about forces. Think what we said about forces. Forces have to act in action-reaction pairs, right? There's no other way. So right now, when we stand up, gravity is real. That's a force acting between me and the earth.
How does the car, the window?
How does that? So when you go around the corner and you're pushed into the door of the car, let's say,
Yeah.
or on the outside, what would the forces that are acting be? So is there something out there that's pulling you towards it?
No, you're
Isn't
just
it
trying
the
to go
car
straight
going
and the
this
car's
way
going
and
that
then
way.
you going this way?
Yeah, okay, so really what this is this is a different kind of thing going on here. This is not really a centrifugal force. There's something else happening. What's really happening is that if you were to look from above, like let's say that there's a glass roof in this truck and we're driving along in a straight line. So Delaney's on the outside, we can see her, she's wearing a real bright hat so we can see her, and she's driving along in a straight line. What is what does Newton's first law tell us that she wants to do? She wants to move at constant speed in a straight line, right? And so when the smart aleck turns the car this way and she gets squished against the door, what's going on there? Well, it's not that there's a force that's acting on her to push her outward in the car. She wants to keep going straight, and it's the door of the car that's pushing on her to change her motion, right? So the action-reaction pair that's acting is really just you're pushing on the car and the car is pushing on you, right? That's it, on the door of the car, okay? So in order for objects to travel in uniform circular motion, like this person right here traveling around this center point, right, there has to be some means of providing that centripetal acceleration. There has to be some means of providing the acceleration that's going to change this person's motion from being in a straight line to being curved. What's providing that?
The wall.
Yeah, we might call it the floor, right? The outer wall of the space station, what we might call the floor, is providing a normal force that pushes that person towards the center. And the proof of that would be if the floor were not made very well, and if there were structural defects, and the thing spun a little too fast, that person could break through the floor and just end up shooting out into space. That would be a bad outcome, but right? I mean, but that's you get that could happen, right? So the floor is what's providing that centripetal acceleration. Okay? So there has to be some means. If I have a rock tied to a rope and I spin that rock around on the rope, it goes in a circle until I spin it so fast that the string snaps, and then what's it do? Shoots off in a straight line, right? Well, hopefully not. Okay, so let's study this a little bit. So now we've got this circle here is intended to be, let's say that we've got some object out here. We'll just make it a rock on a string, how about? Okay? The rock's on the string and it's going around in a circle. And so this, you can't see that, but that says R0. So that's the initial position of this rock, okay? A little bit later, it's going to be at a different spot. So let's go ahead and let's create another point. Let's see, I'm going to do this. I got to do construct. Oh.
You already have a dot on there.
I know, but I want another dot on there. Construct point on circle. Okay, so where's my other? They're right there. But I don't want them over there. I want them about over here. Okay? And now let's construct these 2 points, and we'll construct a segment. And that segment is going to be blue.
I like it pink.
You like it pink? Tough.
Oh,
It's blue.
See, pink is better. You chose blue.
Okay? Oh, it's different blue. Oh, well, good enough. Okay, and this one, let's label these points. So that point and that point we'll label. Show labels. And let's even go ahead and label that guy. Show label. And I don't like the label K. I'm going to call that,
D.
I'm going to call it R for R final. Okay, everybody see that?
Mm-hmm.
Okay, so those are the position vectors at time 0 and sometime later when this guy's moving around the outside of this circle, or this rock is, right? Okay, now let's do something else. I'm going to define you tell me, what's the velocity vector going to look like, my initial velocity vector going to look like right there? In what direction is that rock moving at that particular time? Okay, it is. It's tangent to the circle, isn't it? Right? It's, oh, what happened to my pens? Okay. Have I taken roll? I don't think I did, but I better. Michelle, Sydney, Ryan, Alexis, TJ, Brady.
Just gonna ignore that. Oh, is he?
We use it in geometry.
I just know how to find it, I don't know what
I
it
use
is.
it in geometry.
Yes, you may. Okay. So, would you guys agree that at that one moment in time right there, this person is moving tangentially? Right? If I just freeze, if I want to look at the velocity vector right here, this person is moving in that direction. They want to continue moving in that direction, but the string pulls them towards the center and changes the direction, right? Okay? So it would look then, I want to take this point, oops, not that. I want to take this point and that segment, and I'm going to construct a perpendicular line, okay? And let's make that very unobtrusive like that, okay? So then I just want to pick for my velocity vector, I'm just going to pick I need to pick a fixed length. Let's just say that the velocity is, well, it's this big. So it's going to be this long. Okay, I'm going to construct, whoops. I'm going to construct a segment, and I'm going to make that segment red, and I'm going to make it fat. There it is, right? Everybody agree that's tangential? Okay.
What does that mean?
Meaning that it's that blue line is a tangent line. It only intersects the circle at that one spot.
Okay.
Why did you make a second circle?
I made that just so I could get a length that's going to be consistent. I'll make it go away in a second. So I'm going to measure the radius of this circle. Radius. Okay, and there's my radius of that circle. Okay. So sometime later, imagine that's a vector though, right? That's an arrow on the end. Let's pretend. Okay, so sometime later down here, the speed's going to be the same. Okay, so I want to do the same thing. I want to draw another circle with that radius. So I'm going to construct a circle by center and radius, and there it is. Okay? And so we want to find now, we want to do another perpendicular line there to get our other tangential velocity vector. And let's label these, by the way. We'll call this one, we're going to call that
Just so you
V naught.
know, just so you know, you have 4 minutes left.
Oh, that's all I have? That's so dumb. Why don't they just give me way more time? I need way more time to do this important stuff. Okay, that label's in the wrong spot. Can't move that label. That's not good. Oh well. That's okay. That's V.
Okay.
So now we're going to do the same thing here. We're going to create a perpendicular. Construct a perpendicular
What are
line.
we trying to find?
You'll see. Okay. So there's my other perpendicular, and now we're gonna find this intersection, right?
Okay.
So I need a point right there on that intersection. And I'm gonna construct that segment, and we're gonna make it red
Pink. Oh.
and white. Okay, now we can probably get rid of some other stuff, right?
Yeah.
Let's get rid of this. Starting to look confusing. Let's get rid of that, and that. How? Whoops. That.
Goodness, 2
Done
minutes.
did
Oh my
it.
god.
That. And we'll hide those. Okay, so they go away. But look what this does now. This does some interesting things. As I tweak this circle, everything kind of stays in place, doesn't it? right? Okay, everybody buy that?
Yeah.
Okay. That's probably where we have to leave off for tomorrow.
Okay. What does that matter though?
Oh, you'll see.